Hello everyone, this is Mike Dowding with the SD Mines Physics Department, and we are moving on to chapter 27, which is circuits. And in the previous chapter we covered resistors, resistance, and resistivity. And from that previous chapter we learned that the resistance of an object was based on the resistivity, length, and cross-sectional area, where the resistivity was a materials property of our resistor. And so what we're going to do now is we're going to take the knowledge that we have about resistors, current, electric potential through Ohm's law, and we're going to start putting this material together into circuit diagrams. And just to refresh our memories, we will need a source of electric potential, and so that is going to be our battery. And we've used batteries before back in chapter 25 with capacitors, and so this was the source of our positive and negative charge. And then we also need a symbol for resistors, and those are going to be the zigzag lines. And these can be drawn horizontal, vertical, sideways, however you want. It's going to be really important, though, that we draw these circuits in such a way that we can kind of keep track of things. And so the first thing that we're going to do is just a quick refresh on Ohm's law. If I have a battery and I hook it up to a resistor, that battery is going to provide charge, which will then travel through the circuit as current I. And that amount of current is going to be determined by how much potential we have versus the resistance of the resistor. So in other words, the current in our circuit is going to be determined by that ratio of potential to resistance. And in the last chapter, chapter 26, we learned that resistors can produce heat, and as they get hot, the resistance value goes up. But for these circuit examples, we're going to go ahead and assume that the heat that's generated is small enough that it's not really going to have all that much of an effect on the resistors themselves. So that's a pretty straightforward problem. If we wanted, we could put some numbers to this. Maybe we have a 20-volt battery and a 10-ohm resistor. So what would your current be? Well, in that case, 20 over 10 is 2, and the units that we have for current are amps, and so we're done. Well, we want our circuits problems to be a little more interesting than that. So let's take two resistors, and we'll connect them one after the other. So this is our series combination. I'll go ahead and hook up a battery, and I'm going to use two different resistors. For the first one, I'll use 100 ohms, and for the second one, I'll use 200 ohms. And for the battery, we'll say that our battery is 50 volts. I'm just throwing some numbers out there. And so what I want to know, what is the potential difference across each resistor, and how much current is passing through each resistor. And if we go back to some of the discussions that we had in chapter 26, Remember that for our battery, the rating on the battery measures the change in potential across the two nodes. And so getting from this top plate of the battery to the bottom plate of the battery is where we get our 50-volt difference. But it shouldn't matter if we go from the top plate to the bottom plate directly, or if we take a more roundabout path. In other words, the potential difference across these 2 points has to be the same regardless of the path that we take through the circuit. And that means that as we account for the potential difference across the first resistor and the potential difference across the second resistor, the combination of those two must equal the potential difference of the battery. And that's going to be our first step towards figuring out this circuit problem. So I'm going to clean this up a little bit. We can always add this stuff back in later if we need to. The other thing that we need to know is current. Well, I can see the battery, and I know that current is the flow of positive charge, which means that any current coming from the battery is going to have to travel in this direction. But that current only has one path through this circuit. That current has to go through resistor 1, and then it has to go through resistor 2 before eventually returning back to the battery. So that means that our two currents, I1 and I2, are actually the same current. They both have the same current of I. And this is going to be the first principle or concept of resistors in series. So resistors in series are going to have the same current. Now, from Ohm's law, we know that there is a relationship between potential difference, current, and resistance. And if we modify this equation to consider only resistor 1, then we have the resistance of resistor 1, which is 100 ohms. We have the potential difference across resistor 1. So going across resistor 1, there was that potential difference. But then we have the common current value that's going to be running through both of them. Likewise, if we apply Ohm's law to the second resistor, well, our second resistor has a resistance value of 200. There is going to be some potential difference across resistor 2, but we have to have the same current I running through there. And so this information is going to be moved up into the equation that we just made with respect to the battery. And what this allows us to do, since potential of resistor 1 plus potential of resistor 2 has to equal the potential of the battery, we can now make the necessary adjustments. We can factor out the unknown current of the circuit. And since we know what the two resistor values are, and we know what the potential of the battery battery is, then we can solve for the current that is running through our circuit. So we had a potential of 50, resistor 1 was 100, resistor 2 was 200, so I have 50 divided by 300, which is going to be 1/6 of an amp. I don't feel like getting my calculator out right now, but 1/6 of an amp is what we have for the current running through our circuit. Well, now that we know what the current is, we can come back to our individual potential expressions. We can take our current of 1/6, we can multiply it by the value of the first resistor, and that will give us the potential difference across the first resistor. So now it looks like I'll have to take my calculator out, because we have 100 over 6, and that's coming out to be about 16.7 volts. And then I'll go back and I'll do the same thing for V2, except I should already have a pretty good idea of what V2 is, because I know the potential of the battery was 50. I know that I've already used up 16.7 volts going across the first resistor. And so what's left over is 33.3 volts. And we can confirm that by taking our equation for V2, plugging in the current that we solved for, and then multiplying by resistor 2, and, well, lo and behold, we do get the 33.3 volts. So that's a very basic series resistor problem. And what I'm going to do here is just make a little bit of space for myself, because I want to put another set of concepts here. Even though our resistors had the same current, they will have different potentials. So V was the potential of each one, and we just solved for that. We had V2 was the 33.3 and V1 was the 16.7. Now that's not too much work to do to figure out the current and the individual potentials, but what if we had a circuit with, say, 100 resistors connected in series? This math is going to take us quite a bit of time. And so what we want to do is consider what we did back in the capacitors chapter. Can we take this circuit, which has multiple resistors in it, so we'll consider the same two resistors, and can we remove those resistors and replace them with one equivalent resistor that will do the same job? So we did this quite a bit with the capacitors, finding equivalent capacitance. So now we're going to find equivalent resistance. And when I say that this equivalent resistor needs to do the same job as what the first two did, what I'm really referring to is how much current will be drawn out of the battery. So I want this equivalent resistor to draw the same amount of current out of the battery as what the combination R1 and R2 did. And yes, we do know what that current needs to be, but we're going to hold on to that and pretend that we don't know. So again, we're going to go back to the equation that said the potential across resistor 1 plus the potential across resistor 2 has to equal the potential across the battery. And I will substitute in the same expressions that we did up above. So the same current I is going to run through both resistors, and that has to equal the potential of the battery. But here's where I'm going to switch things up a little bit. Instead of plugging in the value of the battery, I'm going to look over here at our equivalent resistor circuit and ask Ohm's law what's going on. Well, Ohm's law says that I have current I running through the equivalent resistor, and that would equal the potential across the equivalent resistor, except the points on either side of that equivalent resistor are connected directly to either side of the battery. And so the potential difference across our equivalent resistor is actually the potential of the battery. And this is the whole idea behind finding an equivalent resistor, is that it will automatically have the potential of our battery. So I'm going to bring that down here and replace the potential of the battery with the information that we have about the equivalent resistor, and now, surprisingly enough, we have an equation that tells us what the equivalent resistance is going to be, because the current is now common to every term, so that's going to cancel out, and we just end up with a direct summation that tells us what the equivalent resistance of the circuit is. So resistor 1 was 100 ohms, resistor 2 was 200 ohms, so that means that resistor 3 has to be 300 ohms. Now, where is the self-check? How do we know that we have the right answer? Well, we're going to take that back up to this equation that says we hooked this equivalent resistor of 300 ohms up to a 50 volt battery, and that results in, well, 50 over 300, that's 1/6. So we are in fact getting the same outcome, but by finding the equivalent resistance, we can actually get to our answer of what the current needs to be a lot quicker. And then if you can imagine, whoops, I didn't want all of that to go away. If you can imagine what would happen if you had about 10 or 15 resistors in series, well, they all have to have the same current running through them. And so I would just end up with a summation of all of my resistor values until I got my equivalent resistance. And that right there is the key. To find the equivalent resistance of resistors connected in series, we just take a direct summation of those values. And I'm going to put that right here with the other concepts for resistors connected in series. And we are going to come back to these three little notes time and time again when it comes to solving these resistor problems. So we'll go ahead and put this to the side for now. That's how we deal with resistors in series. So now we need the other case scenario, which is resistors in parallel. And the definition of parallel is going to be the same as what it was for the capacitors. We're going to have two resistors with their heads connected at the same location and their tails connected at the same location. We'll go ahead and call this resistor 3 and resistor 4, and then we need to connect those to some kind of a battery. And this is where drawing the circuits, you have a little bit of liberty as to how you can draw these circuits. Personally, I would not have drawn this circuit in this fashion. I would have drawn it this way. Sorry, that was resistor 3. I would have drawn it this way. And this is where realizing the connections in your circuit becomes all the more important, because on this diagram we need to consider what our current is going to do when it comes out of the battery. So our current's going to come up, and then it's going to hit this intersection, and some of the current will go through resistor 3, some of the current will go through resistor 4. And then those current values will come back together at this bottom intersection and continue back to the battery. Well, is there any difference between that diagram and this diagram in terms of the current? And the answer is no, because when the current gets to this intersection, some of it is going to branch off and go through resistor 3. The rest of it is going to branch off and go through resistor 4. And then they will come back together at this bottom intersection and continue on to the battery. Well, in addition to that, if we look at these two resistors, the definition that we have for parallel says that the heads of the resistors have to be connected together, the tails have to be connected together, and they are. But the heads of these two resistors are also connected to the head of the battery. The tails of these two resistors are connected to the tail of the battery. And so right away, that tells us that all three of these points right here are actually just one single connection in the circuit. And all three of these points here are just one connection in the circuit. In other words, resistor 3 is connected directly to the head and tail of the battery. And if I put a value for the potential of the battery in here, well, if the battery is 100 volts, then that means the potential across resistor 3 is 100 volts as well, because what is resistor 3 directly connected to? The battery. Likewise, what is resistor 4 directly connected to? The battery. So everything here ends up with the same potential difference. That's going to be our first concept for our resistors in parallel. Maybe I can put those up here. So resistors in parallel will have the same potentials. Not Sam. So resistor 3 has the same potential as resistor 4, but does that mean that resistors in parallel are always going to have the potential of a battery? And that answer is no, because if I take that battery away, if we don't know that there's a battery there, does that change the fact that these two resistors are still connected in parallel? And the answer is no. So it's possible that I could have other things connected to these two resistors besides a battery. But that doesn't change the fact that the potential across the two is going to remain the same. This is just a special case scenario that we happen to be connected directly to a battery. And so we luck out in that we automatically get the values for V3 and V4. Now, because of that, because we lucked out and we got the values for the potentials, if I put in some resistor values, say 300 ohms and 400 ohms, I automatically get the values of the currents that are going to run through each of those resistors, because Ohm's law says the potential across resistor 3 has to equal the current through resistor 3. But I already know what potential 3 is. It's 100 volts. I already know what resistor 3 is. It's 300 ohms. And so current 3 becomes 1/3 of an amp. For resistor 4, Ohm's law says potential difference across resistor 4 is current 4 times resistor 4. But we already know what potential 4 is. It's 100 volts. And we know what resistor 4 is. It's 400 ohms. And that's going to give us 1/4 of an amp. And from this, what we can do is we can extrapolate what the current coming out of the battery is. Because we said once that current reaches this intersection, some of it is going to branch off and travel through resistor 3, some of it is going to branch and go through resistor 4. And so now I'm going to get my calculator out, because I need 1/3 of an amp plus 1/4 of an amp, which is approximately 0.583 amps. So that's the total current that's coming out of the battery, and then it's distributed through those two resistors, and then those currents add back up and return back to the battery. Well, if we can do equivalent resistors with series systems, there's really no reason why we can't do an equivalent resistor with a parallel system. So we'll make ourselves a fresh sketch here of the system. And we'll go back to what we know. We know that there's some total current that will come out of the battery. That total current will split into current 3 and current 4. And that provides us with an equation. This is actually what is known as conservation of current. So what current came in to this intersection has to exit the intersection. So we have to be able to account for all of the current at any given intersection. We know what each of those currents is, but for right now we're going to pretend that we don't, because if you remember, the goal of an equivalent resistor is to do the same job as what the other two resistors did. And by the same job, what we mean is the current that is drawn out of the battery. We'll go ahead and apply Ohm's law to this equivalent circuit. We have some unknown equivalent resistance, but that equivalent resistance will have the total current from the battery passing through it. And just like the other equivalent resistor diagram that we saw from the series case, the potential difference across this equivalent resistor is the potential difference across the battery. Now, I know what the potential for that battery is. We had a value of 100 volts. And I know what the two resistor values are, but, well, it looks like there's a lot of unknowns in this system. So the next step that we're going to take is we're going to take this equation up here that we know has to be true if we're going to conserve all the current in this circuit. Then we know that the total current has to equal current 3 and current 4. Well, Ohm's law for resistor 3 says that current 3 has to equal the potential across resistor 3 divided by resistor 3, except that both resistor 3 and resistor 4 have the same potential. And that is going to get substituted into this equation. Likewise, Ohm's law for resistor 4 says that current 4 will have to equal the potential across resistor 4 divided by resistor 4. But again, this is the same potential as the battery, and so this will get substituted in for I4. So I total now equals V over R3 plus V over R4. And the last thing that we want to substitute is, the equation that we get from Ohm's law for the total current. And the total current going through that circuit using this Ohm's law expression here says that current total will equal the potential of the battery divided by the equivalent resistance. And from here, we lose all of the potential values, and we're left with not a summation of the resistance values, but an inverse summation. 1 over the equivalent resistance of the circuit can be found by taking the summation of 1 over each individual resistor value. And so this is how we're going to find our equivalent resistance. Where did I go with my... So resistors in parallel have the same potential. They have different currents, and to find the equivalent resistance, we have to take the inverse summation of all of our resistors, but then don't forget to invert your answer. Okay, time to put all this together. So the equivalent resistance of this circuit should be 1 over R3, which was 300, plus 1 over R4, which was 400. Back to the calculator. 1 over 300 plus 1 over 400. And this is giving me 0.00583 repeating, but this is not our equivalent resistance. This is the inverse of our equivalent resistance. So I'm going to take that 0.0058 and I'll use it to divide 1. And when we do that, we get a value of 171.4 ohms. So this is the equivalent resistance for our resistors connected in parallel. And this equivalent resistance is completely independent of the battery that we are hooked up to. But let's go ahead and hook it up to the battery. Remember, our battery was 100 volts. We now have an equivalent resistance of 171.4 ohms. That is going to draw some current from the battery. That will be our total current. And that total current will come from the same Ohm's law representation that we had before. We have 100 volts, 171.4 ohms, which gives us surprise, surprise, 0.583 amps. Exactly what we got before. Getting to this answer took us quite a bit longer than the first solution that we did. And I would agree 100%. The first way that we solved this was a lot easier. But, once again, we only have 2 resistors connected in parallel. What if you had 10, 15, 20 resistors connected in parallel? In that case, it would be a lot easier to start over here with finding the equivalent resistance of your circuit so that you could solve for the, sorry, this looks too much like a C. That should be I. So it would be a lot easier to start here to find the equivalent resistance, solve for the total current, and then work our way back to find the individual currents for each resistor. So in summary, let's come down to a clean spot on the screen here. We're going to say resistors in series and resistors in parallel have the same current. They have different potentials, and the equivalent resistance can be found by taking the direct summation of all the resistors. For parallel, the resistors will have the same potentials, different currents, and we have to take an inverse summation of, hold on, start over with that. We have to take an inverse summation of all of our resistor values to get the inverse of our equivalent. Now, if this looks really familiar to the capacitor systems that we worked with, you're not far off. And for comparison, I'm going to go ahead and write out the series and parallel information for capacitors, and then we'll compare the two. So for capacitors in series, if you remember, capacitors in series have the same charge, but different potentials. And capacitors in parallel have the same potentials, but different current. I'm sorry, I'm still thinking resistors here. Different charge. Well, so far that doesn't really look any different from what's happening with the resistors. The only major difference is that capacitors store charge, resistors allow the charge to pass through. However, if you look back in your notes from chapter 25, when it comes to finding the equivalent capacitor for a series capacitor system, it was the inverse summation of the individual capacitors that gave us the inverse of the equivalent capacitance. And it was the direct summation of the capacitors that gave us the equivalent capacitance of the parallel combination. So I wanted to write these sets of information side by side so that we can see, yes, there are some definite similarities, but there's also some very critical differences. The means in which we produce the equivalent values are opposite for the capacitor and the resistor systems. So we need to be really careful about how we do our summations in these circuits, because they're not the same as what it was for the capacitors. So I'm going to stop this video here. In the next video, what we're going to do is we're going to start looking at more complex combinations of resistors. So I'll just jot down a quick little circuit here. So 6 different resistors, they're connected to a battery of some voltage. And what I want to know is everything. So what is the current passing through each resistor? What is the potential difference across each resistor? How much current is being drawn out of the battery? And if possible, can we replace all of the resistors in that circuit with one equivalent resistor that will do the same job? And the answer is yes. The trick is, how do we get from this diagram to this one? Because not everything in this circuit is connected just in series or just in parallel. There seems to be a combination of the two. And if you remember from your capacitor circuits, we did have a way of slowly stepping through the circuit, reducing down to a single equivalent, and then backtracking our way to the original diagram, finding all of those values that I listed, all the potentials, all the currents. And what we're also going to do at that point is we're going to talk about power. And back in Physics 1, if you remember, power is the rate at which work is done, but work is a change in energy. And so I would like to know, as current passes through all of these resistors, how much energy is being dissipated by those resistors. Because one of the things that we said happens with a resistor is that they'll heat up and they'll give off some thermal energy. And so giving off of that energy in a certain amount of time, well, that's power. All right, so that's what we have to look forward to. I'll go ahead and end things here, and I'll see you at the next video.